a calculator, a PI pad calculator, and I checked out the values of the resistors from the schematic, and it actually turns out that if I use this calculator, for example, if I put a 20 dBs of attenuation and I ask the calculator to generate the actual values for 50 ohms inputs and output impedance, it says 247.50 and 61 ohms, okay, 61, 61, 247 and 50, and here we have 62, 62 and 240 ohms, and it's the same for all the other pads. For example, for the 4 dBs, let's do the 4 dBs also. It says 23.8 and 220, so we are at 220 and 24, pretty close the values, never precise, and I wonder why. I think there were precise resistors back then, but they have chosen a little bit off the resistances. But anyway, it should not matter too much. We should expect a little bit of inconsistency, let's say, from the actual values, but maybe they're measuring also things internally about parasitic resistances in those switch terminals. I don't know. But anyway, I'm gonna use the values of the actual schematic. I was just about to try to find 0.1% of resistors, but since these resistors here do not actually match exactly to that amount, the calculated values, I think I'm going to go with cheaper 1% resistors, because it's 1/3 the value of the money. So for 18 resistors, it's something like €5 in total, and if I go to 0.1%, it's something like €16 or something like that. So I think there's no need to go that precise, because this attenuator is not that precise anyway. It can be 1.1 dB, for example, in the 1 dBs, or 4.1 or 7.9 instead of 8 dBs. So I don't think I should spend that much in so high precision resistors. It won't matter that much, I think. A good an idea might be to try to find the exact resistors that this calculator here shows, just to try to be as precise as possible. But again, in practice, it doesn't matter if you're out 0.1 dBs. Okay, in most applications, it really does not matter. But if you're out in half dB or 1 dB, yes, that's a little bit more, but it does not matter for most applications. Okay, so yeah, I'm gonna order these resistors and fix this now that I know that these pads are actually for 50 ohms input and output impedance. I know that the attenuator is a 50 ohms attenuator, and I'm going to change these resistors, these carbon composite resistors that have drifted way off, and because the new resistors that I'm going to order are also good quality, they are VC resistors. I think I'm going to order a 1/4 watt resistors because they fit nicely, and I think those resistors in here are also 1/4 watt, judging from their size. So everything will turn out well, I think, and those new VC resistors, they really don't drift at all. No comparison with the carbon composite resistors. They don't drift. They're just very dependable and reliable. So hopefully this will make an attenuator that will be in use for the rest of the life here. So let's order this resistor and raise these resistors and see how it goes. So it's been about a week since I posted the previous part of the video. In this video, of course, it's a few seconds, but it's been about a week and I was waiting for those resistors here to arrive. These are VC resistors mostly, very nice quality, 1% resistors, and I have replaced these resistors in this attenuator, and now I'm gonna close the enclosure and test it to see how it performs. Here we go with the test. I have set up the generator here on a frequency about let's say it's this range here, 1.6 to 3.6. we are at 1.6 to 3.6 and we are at about a little bit less than 2. What is this? Yeah, 2.1, 2, 3, 4, 2.4 megahertz. So I have connected this with a very high quality Tektronix cable, which has a very low loss at these low frequencies, and on the attenuator, and then with another cable of moderate loss to the oscilloscope. And I'm testing it at such a low frequency because I know that this oscilloscope with those analog plugins can cope right with this frequency. So here we go. We have set the generator for exactly 2 volts peak to peak. We are at 0.5 volts per division. So we are at exactly 2 volts peak to peak here. Now 2 volts peak to peak is 10 dBm. Okay, I'm currently also doing the calculations here with this JavaScript conversion calculator to help me out. So 2 volts peak to peak is 10 dBm. Right, so I want to test now the first 2 attenuators. I'm switching on the 1 and the 2. So I have attenuated this by 3 decibels now. And if I attenuate 10 dBm by 3 decibels, it's 7 dBm. Okay, and according to this, 7 dBm should yield about 1.415 volts peak to peak. So we should see here 1.415 volts peak to peak. So let's see, let's turn this a little bit. Yeah, 0.2 volts per division, and see, reposition it, and we are 0.2, 0.4, 0.6, 0.8, 1, 1.2, 1.4, and 1.442, something like that. Okay, we're just about right. So next step, I'm gonna switch it again. Now I'm gonna test the 2 and the 4. So I'm switching now at an attenuation of 6 dBs from the original 10 dBm. So that will be a 4 dBm, and I should be able to read that about almost exactly 1 volts peak to peak. So we're again at 0.2 volts per division, and let's bring the beam here. Alright, so 0.2, 0.4, 0.6, 0.8, 1 volts peak to peak, exactly. So next step, I'm gonna switch this off again, and now I'm gonna test the 4 plus 8. I'm gonna test the 12 dBs. Alright, so this is 10 dBm here, plus, minus 10 dBs, minus 12 dBs, it's minus 2, minus 2 dBm, which is 0.5 volts peak to peak. Now let's see if this is 0.5 volts peak to peak. I can also increase the accuracy here by switching to 0.1 volts per division. So let's see, is it 0.5 volts? 0.1, 0.2, 0.3, 0.4, 0.5, just a little bit here. It might be a little bit of miscalibration of the scope or a little bit out the attenuator here, because we have rounded the values. Tektronix has rounded the values here actually. If you calculate this attenuator based on the dB values of attenuation with online calculators, the values are just a little bit off of these resistors, but they're close enough. So I expect here to see a little bit off. But again, we are 0.1, 0.2, 0.3, 0.4, 1 volts peak to peak here. So very fine job here. Now I'm gonna switch this off and I'm gonna switch to 16 decibels of attenuation. And we're going back to our calculator, and we had 10 dBm from the generator, and we want now to attenuate by 16 dBs. So it will be let's do it just to make sure. 10 minus 16, just to make sure we don't do any mistake. It's minus 6 dBm, and minus 6 dBm here should yield in a voltage of 0.317, 0.32 volts peak to peak. Now let's see, let me bring the beam a little bit here. So we are at 0.1 volts per division. It's 0.1, 0.2, 0.3 and something. I can see here a little bit increase the illumination. 0.3 plus 2 or and just a little bit more maybe. Okay, so we're fine here. Now final step to check the 20 dBs of attenuation, and this will be 10 dBm minus 20. It will go to minus 10 dBm of signal, and minus 10 dBm will be 0.2 volts peak to peak. So let's check if we are at 0.2 volts peak to peak. We're at 0.1 volts per division, 0.1, 0.2 exactly. So very fine job there, very fine job in this attenuator. We have managed to fix this and correct the way drifted the values of these resistors here inside this attenuator, and we're still using a very good quality resistors inside and quality parts, but we have corrected now and made this attenuator usable to 50 ohms. So yeah, I think I'm pretty happy with it, how it turned out, and I always keep my old resistors that I replaced in a box and as a training kit actually, to train maybe the kids or some friends, make some quizzes maybe, who knows, of what the fault of each component is. So I keep all the faulty capacitors, all the faulty resistors, relays, and all the faulty components in general as a training, to make little training sessions for newcomers to the repairs hobby. So that was it, and thanks very much for watching. I hope you enjoyed this video, and we're actually making high quality attenuator here that can go up to 51 decibels of attenuator. And I have to say that the attenuator, since it was taken out of a Tektronix 491 spectrum analyzer, which is this IF attenuator, I expect also this attenuator here to be way off. Okay, I expect those resistors, those carbon composite resistors, to have drift. So yeah, another lesson here those resistors can drift way low.